Hello students. So in today's lecture we'll be discussing about the group action of piles, uh, the load carrying capacity, how you determine the load carrying capacity of a pile in field, and also uh, a special terminology called the negative skin friction, and what are the situations where that phenomena is experienced. So we already discussed about the capacity of single pile. Now we let us see how the piles perform when they are in groups. So in when piles are arranged in groups, they can be arranged either in a square pattern, rectangular pattern, triangular pattern, circular. A lot of patterns they can be arranged. Now why we arrange the piles in groups? Because based on the loading conditions, that the type of load coming from the superstructure allow us to design either it is a triangular group or a circular group. Based on that we arrange, considering the design as well as the economy, everything. Now what we do is we cut the head of the piles for this at the same level, and then we install the pile cap. So this particular structure is the pile cap on which we construct the column on which the entire building loads are coming. But if it is a bridge or something like that, then we call it as a pier here, or a column, whatever it is. So when piles are grouped, they are grouped by means of a pile cap. So the pile cap, on top of that pile cap, the entire load will be coming, and that will be transferred to the piles. But the very interesting thing is that when there is only one pile, the pressure developed around the pile will be less, whereas if we have a group of piles, then definitely there will be overlapping of the pressure bulb. Already we discussed about the pressure bulbs. So that pressure bulb will overlap, and this overlapping zone will have more pressure, and it can lead to the greater settlement or the settlement of the soil. So we must be very careful about determining the capacity of group piles. So now let us discuss. There are two cases, as in the case of capacity of single pile. In group pile also we have the piles in granular soil, as well as we have the piles in clay soils. In piles in granular soils, it is straightforward. That is the group. The ultimate load capacity of the group is N into QU. That's where N is the number of piles in that group, and Q is the ultimate load carrying capacity of a single pile. So that is the equation for piles in sand or gravelly soil, cohesionless soil, where NQU multiplied by eta, which is the efficiency of the pile group. So efficiency is generally it is greater than 1 in sands. Now let us see the spacing of piles. Usually we take 2.5 times the diameter for N bearing piles, and 3 times the diameter for friction piles, and for piles on rock it is 2 times the diameter. And efficiency is equal to 1 if the spacing is ranging from 5 to 6 D in case of sands, and efficiency is 1 if the spacing is 8 times D in case of clays. So this is a general expression. If you are given asked to find the group capacity of piles in cohesionless soil, just find the individual capacity, then multiply it by the number of piles, you will get the group capacity. And also to find the efficiency, you have another equation given by Converse-Labarre formula. The formula is called Converse-Labarre formula, and it is given by eta is equal to 1 minus theta by 90 into n1 minus 1 into n2 plus n2 minus 1 into n1 divided by n1 n2, where n1 is the number of rows of the piles and n2 is the number of piles in each row, and theta is equal to tan inverse capital D by small d, where small d is the center to center spacing of the piles and capital D is the pile diameter or width. So just I will show you how they are arranged in groups. So this is a group. If this is a group, then this is the center to center spacing between two piles, and this is the number of rows. So how many rows are here? 1, 2, 3, 4, 5. 5 rows are there. And how many piles are there in a single row? You have 5 piles. So this is a 5 by 5 arrangement. So that if you know the N1, N2 and the capital D, that is the pile diameter or width in case of square pile, and you have the center to center spacing of the piles, then definitely you can find the efficiency. Now moving on to the pile groups in clay soil. Here the analysis is slightly different. Here what you do is you consider this entire group as a single block and you find the capacity of that block, that pile group block, and also you find the capacity of individual pile, then multiply it with the number of pile and we compare whichever is smaller, that will be considered as the capacity of the pile group. So what you do is to find the capacity of that pile block, this is the equation used. It is similar to the equation used for single pile, but only thing is this CUB is the coefficient at the tip of that pile block and AB here is the area of the block. In previous case we took area of the pile tip and here it is area of the entire pile block. That means if you are arranging piles here in this manner, so this area, that is the area of this block, here it is 5 by 5, so that area will be taken here for this block, whereas here the PB is the perimeter of the block, whereas in the case of previous case we took the perimeter of that single pile, but here in case of group it is the perimeter of that group or that block, and length is the depth of the pile obviously, and Cu dash it is the coefficient along the length. Already we have discussed problems in clay soil, but only slight change here is the area. That means instead of taking the area of that single pile, you take the area and perimeter of that block where the group of piles are arranged. Now let us discuss a problem. So usually for pile groups, most of the questions come for clay strata, because in granular strata the problem is straightforward. You just find the individual capacity and multiply with it with number. But here in the case of clay soil, you need to find the capacity of that group block. So most of the questions will be asked for clay soil as far as pile group efficiency is concerned. So here let us solve a problem. So you are given a square pile group of 25 piles, and that means 5 piles in each row, and you have 5 rows, and the length of the pile is 10 meter in a deposit of 20 meter thick stiff clay. The piles are 50 centimeter diameter at 1 meter center to center. That is the spacing between two piles is 1 meter, and the diameter of the pile is 0.5 meter or 50 centimeter. Undrained strength of the clay at the pile tip is 180 kPa, and the average value of strength over the depth of pile is 110 kPa. That means at the tip the undrained strength is 180, that is Cu value is 180, and at surrounding the pile the C value is, undrained coefficient is 110. The adhesion factor is 0.45. Now you have to find the capacity of the pile group, and the factor of safety is 3. So how will you solve this equation, or solve this problem? So here we know that capacity of individual pile is Qu is the end bearing resistance plus the frictional resistance. So that you have the straightforward equation CNCAP for the end bearing resistance and alpha CAS for the frictional resistance. Just substitute the values, that is C is 180 at the tip, and C is 9 for clay soil. AP is pi r square h, pi d square by 4. So got that. Then QS alpha is already given, adhesion factor is 0.45, coefficient at the around the surface, that is 110, and the area, the superficial area, that is pi d into length, that is pi into 0.5 into 10. So you have the individual capacity here, that is 1095.63 kilonewton. Now what is the ultimate capacity multiplied by the number of piles? So we have 25 piles, so 25 multiplied by this individual capacity, you will get the pile group capacity, that is 27,390.76 kilonewton. Now you must find the ultimate capacity of the pile group as a block. So if you take it as a block, what happens here? This is same, this coefficient for a block is 180 itself, and this NC is 9 again, and you have the spacing of the piles, that is 1 meter. So first find the area of the block. So what is the total length of the block? Length and width here, it is 4 times spacing. So if you see this figure, it is 1 2 3 4 4 times spacing, and you have this distance and this distance. That means here 4 times spacing plus 0.5 means you are taking a single pile diameter as a clearance on either sides. So that is 4s plus 0.5. So that is the length or width, because here it is a square block. So it is 4s plus 0.5 the whole square. So you have the area of block as 4.5 square. Now perimeter of block is 4 times this 4s plus 0.5. So you have the perimeter as 4 times 4.5. Now length of the pile is 10 meter and average cohesion along the length is 110. So now just directly substitute the values. So only change is this area. Here it is 4.5 square and the perimeter is 4 into 4.5. So now the ultimate capacity of the pile group or that block is 52,605 kilonewton, which is greater than the individual capacities when they are summed up, that is 27,390.76. So taking the lowest value, you will be considering this as the ultimate capacity, that is 27,390.76 kilonewton. So the safe capacity is divided by factor of safety, which is 3. So you have the safe capacity of that pile group as 9,130.25 kilonewton. So it is a straightforward problem. Only thing is that you have to check for the pile group capacity. First you find the individual capacity, then you multiply by the number of piles. So you have one capacity. Then you consider the entire system as a block and find the capacity of the block. Then you take the minimum value. That minimum value will be the ultimate capacity of the pile group. Next is a negative skin friction. So what is negative skin friction? So in many situations, what happens is that when the surrounding soil settles considerably, if you are driving a pile, what happens is that after sufficient driving or after construction, when the surrounding soil gets settled considerably than the pile, then there will be a down drag of the pile. So this down drag is termed as negative skin friction. That means you know that the pile always have the capacity of frictional resistance, but there is a kind of negative skin friction which will tend to reduce the capacity of the pile. So this terminology is called the negative skin friction. So generally this happens in a very soft clays and very loose sands. To find the magnitude of negative skin friction, it is similar. You just find the frictional resistance for that particular section where the down drag is happening for that particular depth. So it is, the equations are similar what you do for the frictional resistance, but only thing is that the direction is in the downward direction. So here you can see this is the actual frictional resistance and this is the end bearing resistance, but here in this particular area there is some down drag. That is why it is shown in hatch, and this is the downward. So for this particular depth you find the frictional resistance and give a negative sign, then that will account for the negative skin friction. So here that is what is shown here. So you have the ultimate load QU and you just reduce this QNS for this particular section to get the actual ultimate capacity of the pile, reducing the negative skin friction. So when we find the negative skin friction, we can do some remedies that while before driving the pile, we can have around that portion where that is probable, we can use sleeves, so that will reduce some amount of friction, or we can apply some coating on the pile surrounding the pile, so that will also reduce some friction. And this is possible if you are driving the pile. Okay. So what are the causes of negative skin friction? So what happens is that in case of granular soil, if you have a layer of clay over that, then definitely what will happen, that consolidation of clay will lead to some consolidation settlement, will have a down drag effect. Also, if you have a granular layer on the clay, then also that will have, the granular layer will lead to the consolidation. The granular layer on top of that clay layer will lead to the consolidation of the clay layer, and due to that also there will be a down drag. And obviously in situations where the water table is considerably lowering, and what happens when the water table is lowering, the effective stress will increase. The vertical effective stress on soil will increase. That will also induce consolidation settlement in clayey soils, and as a result of this there will be a downward drag force. So these are the three situations where negative skin friction can occur. So here it is best understood with a figure. You can see here two cases are there, case A and case B. So in case A, you can see you have a clay fill over a sand, and that can lead to negative skin friction, and the vice versa. That is, if you have sand fill over a clay layer, that can also lead to a downward drag. So here, which is contributing to the downward drag here, this clay layer is consolidating, so that will lead to downward drag, and here also this clay layer is contributing to the negative skin friction. So these are the two cases which can be explained by sketches. Now let us move to a pile load test. So in field, when we construct a pile, we must know that how much load that pile will actually take from the superstructure. So for that we have to conduct a pile load test. So in field we have to do number of pile load tests, because based on the soil strata and based on the vast area, you are constructing lot of piles. So unreliability is a main thing that you can't predict. Also the pile load testing also will be different. The soil strata is different, and the construction may change at places to places. The concrete quality won't be same. So we do a number of tests for reliability. Then only we can assure the safe load for the pile. Okay, so we use a hydraulic jack for application of the load. Then what we do is the loads are always applied in steps. That means if the working load, the proposed working load, then 1/4 that load is applied in steps, and always the load test is carried out for at least twice the proposed working load. So based on that you conduct the testing, and you keep on gradually applying this load, and for each load each load increment you measure the settlement of the pile by means of dial gauges. You have around 3 dial gauges fixed, and you take the average value of dial gauges generally. So you apply the load, gradually you increase the load, and you measure the settlement for each load increments, and after a sufficient that desired pile load is reached, you slowly start unloading in the same fashion as you loaded the pile. So this is the arrangement of the setup. That is, you have 2 anchor piles, and you have a beam here, and this is the test pile, and you have a hydraulic jack to apply the load on this pile, and these are the dial gauges installed to measure the deflections or the settlement. And now you can see here, this is the load settlement curve for this pile load test, and you can see here 2 graphs. I will explain what is the first one and the second one. So this is the load settlement curve, and this is the net settlement versus load curve. So I will explain what is the net settlement. So if you have a load Q, the net settlement is calculated as you deduce the elastic settlement from the total settlement. So you have 2 settlements here. Elastic settlement is just the settlement of the pile itself. The pile makes some rearrangement due to that when the loading is taking place. So that is the elastic settlement which happens inside the pile itself. Then the total settlement, overall the pile, how much it is settling in the soil. So from the total settlement you deduce the elastic settlement, you get the net settlement. So here in this figure you have the load on the x-axis and you have the settlement on the y-axis. You can see it is a parabolic variation, and you can see as the loading is increasing, the settlement is increasing, and after considerable increment there is not much increase in the settlement, and after that once the ultimate load what you have decided, that is twice the working load, you start unloading it, and this is the unloading curve. And now from this, how you find the net settlement, that is, So here you can see this is the total settlement ST1 and this is the elastic settlement. So deduce ST1 minus SE1, you get the net settlement. Similarly for this is for load Q1, and when the load is Q2, the net settlement is ST2 minus SE2. So once you find the net settlement, now you again plot the load versus net settlement curve and you compare how the two curves are different. In the first curve you can see after the ultimate load, you can see that the settlement there is no much, there is for a constant load there is the settlement is increasing. See, this load is not increasing but that settlement is considerably increasing. That's almost what is a line parallel to the y-axis or the settlement axis. So you consider where it is parallel to the y-axis, that particular point you take the ultimate load. But there are cases where after the increment again there is some linear increment after the ultimate loading. So what you do is where that linear increment is starting, that is in this curve 2, that will be taken as the ultimate load. So these are the two situations where how we judge the ultimate load. So I will explain it in detail. Yes. So here the first case you have two curves, curve 1 and curve 2. Here you can see the load corresponding to the point where the curve of Q versus S net becomes vertical is the ultimate load. That means this curve between QU and net settlement is parallel to the y-axis that you take as the ultimate load. But in some other cases, still there is a linear variation or linear increment of the settlement with increment of load. So what you do is the ultimate load in such cases is determined from the point of curve of Q versus net settlement where this steep linear portion starts. So where the steep linear portion is starting, that you select as the ultimate load. So this is how we assess the ultimate load. Now how you take the safe load? So there is codal provision according to IS 2911. The safe load is taken as half the load at which the total settlement is equal to 10% of the pile diameter. So you take half load and you check what is the settlement for that half the maximum load, ultimate load. That means half the ultimate load, and also you check the settlement whether it is equal to 10% of the pile diameter. Or what you do is you take 2/3 of the final load and also check the total settlement, whether it is 12 mm, and whichever is less you take that. Okay, so if you measure 2/3 of the final load and what is the corresponding settlement for that final load, and also check whether the total settlement is 12 mm, what is the load for that. So whichever is less, that will be taken as the safe load. Okay, now some other criteria also there where you take the safe load as half to 2/3 of the load, which gives a net settlement of 6 mm. So here you must be very careful. This is net settlement and this is total settlement, both are different. So these are some other criteria. Also one more criteria is there where the limiting settlement is considered. That means the load is taken twice the safe load. The safe load is limiting criteria is if the load must be twice the safe load and the net settlement corresponding to that load shall not be more than 20 mm, and the total settlement also shall not be more than 25 mm. But we always follow the IS guidelines. So for exam point of view, if you are asked to find the safe load in such a case, if you are asked to plot the graph of load settlement curve, generally it is not asked, not that important. Even if it is asked, it is easy. Just plot this curve, this load settlement curve, just plot it. Then you have to follow this guideline. That is, safe load is taken as half the load at which the total settlement is equal to 10% of the pile diameter. That means you take the load, 50% load you take and measure the settlement. Also you check the load for which the settlement is 10% of the pile diameter and you take the minimum load. Another method is again this second point, that is 2/3 of the final load. You know the ultimate load, final load you know, so take 2/3 of that load. Find the settlement corresponding to that 2/3 load and also find the load corresponding to 12 mm settlement and check the minimum load, and that minimum load you take as the safe load. So that is how according to IS 2911 we determine the safe load. Other criteria just for understanding purpose I have given. You need not go in detail regarding the other criteria. Okay, so with that we have completed this fifth module. So in next session we will be starting with the last module, that is the sixth module, where we will be discussing about the soil exploration, machine foundations, etc. Okay, thank you.